Hello everyone, we are Group 6 and today we'll be presenting our Psyche Power Solution project. Our goal was to design and implement a power management system for a rover operating on the asteroid 16 Psyche. Throughout this presentation, we'll walk you through the mission context, our design approach, the control algorithm, and finally, the results from both simulation and hardware validation. To give some context, 16 Psyche is a metal-rich asteroid located between Mars and Jupiter. NASA launched the mission back in 2023 with an arrival expected in 2029. The key challenge for a surface system on Psyche is limited solar energy due to its distance from the Sun, and that constraint alone drives everything in our design. Our project focuses on a hypothetical rover operating on Psyche. The goal is to support science, navigation, and communication tasks under very tight power constraints. So the core problem we are solving is how do we manage limited and variable solar power while keeping the rover operational and protecting the battery? In order to do that, we designed an autonomous power management system inspired by real systems like Mars rovers and the International Space Station.
16 Psyche, a world like no other. To be able to design a rover system, we first have to calculate the power input that we can get on Psyche. So first we consider the distance from the sun. 16 Psyche is much longer distance from the sun. Its rotational period is much faster than Earth at 4.2 hours. Its axial tilt is very dramatic at 95 degrees. So it rotates like a rotisserie chicken on its side. The solar year is 5 Earth years. We then have to take all those things into consideration to calculate the solar radiance using Kepler's equations. We take this every position in orbit into account, including the latitudinal degrees of where the rover will sit. We then have our power algorithm, which takes into account the photovoltaics output, the fault state machine, priority-based scheduling, charging priority, and component degradation over time. Every rover device sits in a tier. We have 3 tiers, tier 1, 2, and 3, based on importance. And we have our interface, which is our GUI from Python. We also have a display shield on our physical device and switches, dry pots, LEDs.
This diagram shows the step-by-step decision process the system follows during each cycle. It starts by checking for a fault. If a fault is present, the system immediately enters survival mode where only essential loads remain active. If there's no fault, the system then checks whether solar power is available. If there's no solar input, the system operates purely on the battery and makes decisions based on the state of charge. If solar power is available, the controller then checks if the battery is also available. When both are present, the system operates in a hybrid mode, where solar power supplies the load first and any excess is used to charge the battery. From there, the system determines how much power is available and passes that into the device scheduler, which decides which loads can run based on priority. So overall, this creates a continuous decision loop that adapts in real time to changes in solar input and battery level. Now, building on that, I'll show how we decide which devices are actually allowed to run. Once the system determines how much power is available, the next step is deciding how to allocate it. Each device is assigned a priority and placed into one of 3 tiers. Tier 1 includes critical systems, Tier 2 includes supporting systems, and Tier 3 includes high power or non-essential devices. The scheduler works by turning devices on in priority order until the available power budget is reached. As power becomes limited, either from low solar input or low battery, the system automatically shuts off lower priority devices first. This ensures that essential functions like communication and control are always maintained. So together, the state machine and scheduler allow the system to adapt in real time while protecting the most critical operations. Now, I'll pass it over to Brad, who will show how this exact logic is implemented across both our simulation and hardware platform.
Now, all of this logic, the tier management, the scheduler, the fault handling, it lives in two places simultaneously. On the left is the Python simulation. It runs a full graphical user interface with two modes. A compressed time simulation mode that can model years of orbital operations in minutes, and a real-time mode that interfaces directly with the hardware. It includes our orbital irradiance model specific to the 16 Psyche environment, a data logger, and a CSV-driven profile for faults and degradation. On the right is the Arduino Giga R1. It runs the same power management algorithm. The hardware gives us physical inputs, potentiometers that act as a radiance control and a maximum battery capacity, toggle switches for fault inputs, and MOSFET outputs that switch LEDs that indicate the various loads. The two systems talk over serial, exchanging data every cycle. The key point in this shared device is the scheduled CSV. The same configuration files drive both platforms. That means you can load the same scenario on the Python side as well as the hardware side using the same device priorities and power budgets without any manual reentry. And here is what this actually looks like running. On the left-hand side is a simulation tab. Your device schedule, your fault profile, your degradation CSV, set the starting state of the change and duration, load the irradiance profile starting point, hit run, and the system steps through the full orbital timeline. The status panel on the right updates live. The battery state of charge, the photovoltaics output, active tiers, which devices are running, and the fault state. On the right is the real-time tab with the Arduino connected. It has the same status panel, same device list, but now the inputs are coming from the physical hardware. You can see the actual board in the photo, the display shield, the LEDs corresponding to each power tier, and the fault state and the toggle switches. Both modes share the same underlying algorithm, which was the core design goal: one code base, but two execution environments verified against each other. So now that we've shown how the algorithm is implemented in both simulation and hardware, the next step is validating how it performs.
This plot shows the full end-to-end behavior of the rover power management system over one orbital segment, including solar input, battery dynamics, mode transitions, and device scheduling. At the top is battery state of charge. The rover begins near the low power threshold, close to the survival boundary. As solar irradiance increases, the battery recovers and moves into a stable operating region. The middle plot shows power balance between photovoltaic generation, subsystem demand, and battery support. Early in the cycle, demand is greater than generation, so the battery supplies the deficit. As sunlight reaches peak levels, generation exceeds demand, allowing the battery to recharge. This corresponds to normal mode, where all subsystem tiers can operate. Later, as irradiance decreases, the system returns to low power mode with reduced loads. Hysteresis is used to prevent rapid switching near those thresholds. At the bottom, the device timeline shows priority-based scheduling. Lower priority Tier 3 systems are shed first, while Tier 1 survival systems remain active throughout. Fault events are also handled without destabilizing the controller. In conclusion, we developed a complete dual-platform power management system for a Psyche asteroid rover, implemented both as a Python simulation and on Arduino Giga R1 hardware using the same core logic. Results confirm stable operation across normal, low-power, survival, and fault scenarios with reliable mode transitions and prioritized power allocation. This demonstrates that flight-inspired power management can be successfully implemented on practical embedded hardware and validated through simulation.
Thank you for taking the time to listen to this presentation.